All right, everybody, let's get started with our last lecture in CE 312, which is our exam review on this gray and rainy day. Still working on completing the last set of graded assignments for 8.5 and 9.1. Now 9.2, I'm not accepting late work on 9.2 because I just uploaded, like the solution just went active just now. So you now have the solution for every homework in this class, okay? For the grade, you've got the grade distribution right here. I'll put that up there more as a formality because everybody here has a copy of the at-home game, and so you all can play that to your heart's content and figure out what grade you need to get on the final in order to receive a certain grade in the class. One thing I'll mention, the course eval. So right now, the only thing I can see is this in the background, which is how many people have done it. So 19 of you have done it, but only 17 have uploaded the proof to Blackboard that you did it. So I don't know that you did it, right? So there's 2 people in the class who did the course eval, and I don't know that you did it, right? So there's free points out there is basically what I'm saying. So upload a screenshot that you did it, and you'll get free credit, free 10 points on top of your homework average. For the 6 of you that have truly not done it, again, like it's free homework, and I do free homework points. And I do want to hear your feedback. I really do appreciate the feedback. Any questions on logistics? All right, let's talk about the final. Okay, so let's talk about the final. In terms of logistics, the first point I would make is that the final is no more, it's no longer than any of the other exams. I don't create my final exam to be 2 hours long because I have a 2-hour long time slot. It's an exam like any others, okay? The only class where I probably have ever violated that rule is statics because the final's comprehensive. But in here, it's just another exam, okay? It's closed book, closed notes. You can have a calculator and a formula sheet. Also, I think a straight edge will help with things like influence lines. So make sure to bring a straight edge. I do design the exam with my rule of 3. So if I can do it in 20 minutes, you can do it in 60 minutes. And I've given, a final like this before, and what I can tell you that the vast majority of students are walking out well before the time has expired. So I'll be here obviously the whole 2 hours, but it's not intended to be a time crunch, is what I'm getting at. As for the formula sheet, you can do whatever you want on the formula sheet, except for I don't really want to see fully worked out problems. And again, that's more for your benefit than it is for mine. But I do want you to make it yourself. No, just fully screenshotting the slides. I say that I'll collect them after the exam, but probably I'll just look at them because I know some students like to keep their formula sheets for reference for future classes. So I'll let you have them when it's all said and done. I keep the exams, but you can. I keep the finals, but you can have the formula sheets when it's all said and done. Let's talk about the topics on the exam. So the 3 main topics on the exam are influence lines, masthead, and the stuff that we've done this week. For influence lines, make sure that you can construct an influence line, draw an influence line for a response. And so vertical reactions, shears and moments at a given point, fixed support reactions, all that. Make sure that you can use an influence line to ascertain response due to either concentrated loads or distributed loads, and either loads that move or loads that don't. And then make sure that you can use those influence lines to develop maximum response, which is, that right there, that's pretty much everything that we did with influence lines. For masthead, or the computer analysis of structures, I'm not going to make you break out the software. That's not what I'm trying to do. I want to make sure that you understand the software. So I want you to just generally understand what's going on with matrix analysis, but make sure that you understand the operation of how masthead works. So how to create the geometry, how to assign properties, how to define conditions, how to actually run the analysis and post-process the results. So that's really sort of what I'm after, is the conceptual side of things. For the additional stuff, make sure that you can utilize and or derive analysis aids for performing basic structural analysis, and then make sure you have an understanding of tributary area. That's right there is the exam. What I have left in the slides are the greatest hits from the past few lectures. So things like, here are the rules for drawing influence line reactions. So for example, whenever you're drawing the influence line, or the reactions, the influence lines for all the reactions, that's what I want to say. I have a beam here with 3 reactions. Here's all 3 influence lines. You know that the influence lines equal 1 at the reaction of interest, and they equal 0 at all other reactions. They are always straight lines. You know, the hinges serve to change the direction of the line. And that whenever you sum up the quantities along a vertical column, they all sum up to equal 1 if you're looking at all the reaction influence lines. For shears and moments, that's a different story. But if you have just all your reaction influence lines, that plus that equals 1 at every point along the influence line. For shears and moments, I've included the rule for determining the heights, either for shears and moments right here. Whenever you're drawing shear and moment influence lines, again, they're always linear. Again, the hinges serve to change the direction. But the big thing for influence lines for shears and moments is that they always equal 0 at the supports. Okay? If you put a load at the support, the beam experiences no load. So at the support, the influence line for internal shears and moments is 0. Okay? This is just sort of like my general flow chart for matrix analysis. I'm not going to expect you to quote this verbatim, but just make sure you kind of generally understand the idea that whenever you define a model in Mass 10 or really any matrix analysis program, what the model is going to do is it's going to look at each individual element. It's going to write a spring matrix for each element, and then it's going to assemble them into a big old spring matrix, or what we call a stiffness matrix, a K matrix, for the whole system. We do the same thing with the forces, so we write a force vector for all the forces, and then we say, okay, let's knock out the rows and columns associated with the boundary conditions, and then we solve for the displacements. Take those displacements, back substitute them into each element, and boom, we have the whole structure solved. So it's a pretty systematic process for analyzing the entire structure. Make sure you do understand some basics though. So this is the sort of stuff I'm talking about with matrix analysis that I do want you to that I'm really sort of focused on the exam. The term joint and node are used interchangeably. The term member and element are used interchangeably. The idea that you need to adopt a consistent unit system, that kips and inches. This was something that tripped you up on some of the Mass 10 analyses on your project. That a lot of you analyzed the truss in Mass 10 and you didn't convert the joint coordinates to inches. You know, things like our sign convention. Anything to the right is positive. Anything upward is positive. Anything counterclockwise is positive. Tensile forces are typically treated positive. And the reason that we've got to do this is because really all matrix analysis is just writing equations of equilibrium over and over and over again. So when you write an equation of equilibrium, like sum of forces in the y direction, you got to say everything up is positive from a numerical perspective. You've got to choose one of them to be positive. Whenever you're, whoop, that slipped right out of my hand. Whenever you are defining a Mass 10 model, you basically start at the left here and work your way to the right. So you need to define the geometry. So defining the geometry is defining the nodes, defining the elements that go between them, defining the connections. So connections would be like hinges. So once we've done that, we have a model, but there's no properties attached to it. So we need to attach material properties, and we need to attach section properties. So, and the process is that you create the components, and then you attach them to the structure. You then define the conditions of the model. So this is what Mass 10 defines conditions as both the boundary conditions and the applied loads, and they use the term fixities for the support conditions or the boundary conditions. You then perform the analysis, and in really just about all structural analysis programs, it's the most powerful step and the most anticlimactic step at the same time, because you hit this little button called analyze, and it just gives you the answer for the entire structure. It seems kind of nuts that you just hit this button and it gives you the answer. Finally, you can post-process the results. So post-processing the results is just reviewing the results of the analysis. So nodal values and elemental values. So the nodal values would be like displacements or reactions at the joints. Elemental values would be things like the load or the axial force, the torsion, the shears, the moments inside each member. We can also usually plot those as well. I've defined here what nodes and elements are to be more specific. So nodes are where the analysis or where the software is directly going to compute deformation. So the way that matrix analysis works is whenever you're doing a finite element analysis or a matrix analysis, you're directly computing the deformations at the joints, and then you're interpolating everywhere else. And so you generally want to place joints at the support locations, at any internal hinge, at any truss joint, at any point load locations, and what I'll say, all other points of interest. In a linear elastic analysis, that's really just if you're just genuinely interested in a shear moment or a response at a given point. But if you're ever doing a nonlinear analysis or an eigenvalue analysis, the more elements you have, maybe the more accurate your answer will be. So there's actually a science behind that, like how many elements do you need to use to get a given answer. But the way elements work is that whenever you're doing matrix analysis, you break the model down into these discrete regions, and then for each of those regions, you write one of those stiffness matrices I was talking about. And for us, we just have one element per member. So. Whenever you're defining geometry in Mass 10, you just need to adopt a consistent coordinate system or a consistent origin. So if you had a beam that was 100 inches long, it really wouldn't matter. So I've got 4 different options for the X and Y coordinates for joints A and B. And it doesn't really matter which one that you use. Any one of them will work because you'll still end up creating 2 joints that are 100 units apart in the X direction. So as long as you have a consistent origin, you can do whatever you want. And then the last thing, I don't really have anything on structural analysis aids because all that's just sort of derived. But for tributary area, make sure that you understand the tributary area. We're defining that as halfway between adjacent elements. That's what I have for what's on the exam. I'm going to stop talking and start answering. The floor is yours. Yes?
Okay, so you say you didn't have anything on aids. Are we going to have to make up an equation or anything?
That's a good question. So what I'll say is if I need to give you something really esoteric, really like if I require you to use an analysis aid that's really out there, so like some analysis aid of a triangular load or something weird like that, I'll give you the analysis aid. Okay. Now that being said, something basic like a simply supported beam uniformly distributed load, you might want to put that on your formula sheet simply because you could, the homework that you all just did, you used those formulas like WL squared over 8, you used those for the tributary area homework. So that is an aid that I could see you using, okay? Now the other thing I'll mention about analysis aids is if I give you a problem where you need to derive one, well, that's the problem, right? But let's say I give you a structure and I say, use tributary area to find shears and moments, etc. You could just not use them and just analyze the structure directly, and that would be fine too. Again, you got plenty of time, so time's not really an issue. Does that make sense?
Are we going to see the AASHTO vehicle live loading? And if so, are we going to get like the truck or stuff? Yeah.
If you need it, I'll give it to you. That's fine. It's not a bad thing to include on a formula sheet, but I'm not worried about that. I don't expect you to memorize that. If this is a bridge design course, yeah, you need to memorize it. So. Anything on influence lines, anything on tributary area, anything that's coming to mind as something you really were concerned about? Was there anything? How many of you are worried about this exam? I'm just curious. Well, that's good. I like that. How many of you are you're ready for the semester to be over? There's a response. You tell me, do you have any homework problems or solutions you want to look through? Anything in the lecture notes that you didn't understand? Anything? Usually, when we're at this point, the one topic the students tend to be a little concerned about is influence lines. Been a little while. It was before break. It's usually, I think, the trickiest topic that we learn this entire semester. So, is there anything about influence lines that were concerning you or confusing? That's fine with me. I understand it, but I want to make sure you do. So. Oh, wow. Everybody's good. I'm okay to end class early, but I want to make sure you're getting your money's worth. You tell me. Y'all good? You all good? About this third row. Everybody good? Everybody in the back? You good? Okay. Any questions on the exam? From you?
Oh, no.
All right, going once, going twice. I will see you what day?
Monday,
Tuesday.
Saturday.
I will see you Tuesday at 10:15. I'll pull up the code one more time in case anybody missed it. I will see you then.